So today we will learn about the dual simplex method. We know what the simplex method is and we know how to work uh, examples using the simplex method. Okay. Now we will learn about the dual simplex method. What is that? You know, in the simplex method, we first choose an entering variable or entering column or the column of the entering variable. How we choose it? We go to the objective row and find the least negative number in there, right? And that the column where that number is, that column is the departing variable or the column of the departing variable. After that, we go to the column of resources and do the theta ratios so that we choose the row of departing variable. This is the simplex method. The dual simplex method go the opposite way. It chooses first the departing variable, so we identify which row is the row of the departing variable, and then we choose the entering variable. How we do that? We will go to the column at the right, the resources column, and we will find the greatest negative number. Okay? The row of that number is the row of the departing variable. Now, how we choose the entering variable? We will make ratio, but this time ratios are taken as ratios of the entries in the objective row divided over the entries in the departing row we already chosen. Now we will take then the largest negative value in there, which will help us to decide what is the entering variable. Okay, so this is a quick description for the dual simplex method, and we will explain it using the following example, and then later we will explain why we need this method. So, okay, the dual simplex method handles a problem for which it is easy to obtain initial pacing solution that is invisible. So this is the idea. This is the idea. Okay, whenever you have a linear programming problem and you have solution to it, but the solution is invisible. It is easy to get invisible solutions for the problem. In such a case, we will go and use the dual simplex method. Now remember that to use the original simplex method, we always needed to start with an initial visible solution. But sometimes getting such an initial visible solution is difficult. That is why we have a pace 1 form, where we have to introduce slack and artificial variable, and at the end of pace 1, then we get the initial visible solution. So we have to do some work to get initial visible solution. Now we are saying here, if we have a solution, if it is easy to get solution, but it is invisible, then we can use the simplex method. It will help us in such a case. So the invisible solution satisfy optimality criterion, but it is invisible. So satisfy optimality criterion means the entries in the objective rows, all of them are non-negative. So that is the initial table. This says the initial table has non-negative entries in the objective row, but negative entries in the right hand column. So we might have negative entries in the column, but non-negative entries in the objective row. So then we start the dual simplex method. Okay. For sure, example will clarify everything. Consider the following here problem. So this is the original problem here. Maximize z equals negative x1 minus 2x2 subject to these constraints. Now, change each constraint to this inequality and introduce the slack variable to obtain all this is to obtain the canonical form, and this is the canonical form. Now make the table of that canonical form, we get this. Good. Now notice here we have negative values and here non-negative values. So this is the case where we use the simplex method, dual simplex method. And notice here that we have x4 and x5 as initial basic variables. Okay, so the solution to this this table will give us the following solution. X4 is negative 4, x5 is negative 6. This solution is not visible. Okay, and the entries in the objective row show that the optimality criterion is satisfied. So this is the case. This is the case where we use the dual simplex method. Okay, so this is the case. Okay, now we will go back to this example and continue, but let us describe the procedure of the dual simplex method. So the dual simplex method consists of the following steps. These steps are not new for us. Find an initial basic solution such that the entries in the objective rows are non-negative and at least one basic variable has negative value. This is what we talked about. In the column, the very last column, there is a negative value. But in the objective row, no negative values. Okay, now this is the idea. Select departing variable. So here we start with selecting the departing variable. Okay, how we do that? By examining the basic variables and choosing the most negative one. Okay, the most here means the largest negative number. When we use the normal simplex method, we used to go to the objective row and look for the least negative number. Here, we go to the column, resources column, and look for the largest negative number. So, this is the departing variable, and the row it labels is the bivotal row, which is the row of the departing variable. Okay, so we go to the column one and take the largest negative number, then this is the bivotal row or the departing variable. Now how we choose the entering variable? Okay, how we choose the entering variable? Select an entering variable. This selection depends on the ratios of the objective row. So it talks about the ratios, but the ratios of the entries, objective row entries or entries in the objective row to the corresponding bivotal entries. So entries of the objective row to the corresponding entries in the bivotal or departing row. So we will take these ratios. Okay, now the ratios here are formed by only those entries of the bivotal row that are non-negative, sorry. So we will go only and consider the ratios are formed only for those entries of the bivotal row that are negative. So we said take the objective entries in the objective row, make the ratios, but do these ratios only for the negative entries in the departing row. Okay, now what happened if all entries in the pivotal row are negative? The problem has no visible solution. Okay, what if there is no negative number in the pivotal row? Then we have the conclusion there is no visible solution. Then we are done. Okay, now what if this is not happening? Say some entries are negative. So what we do? Select the maximum ratio. And here we will select the maximum ratio. In the simplex method, we use the minimum ratio. Here we select the maximum ratio because this ratio will be negative. So we will select the maximum ratio. The column for which this ratio occurred is the pivotal column, and the corresponding variable is the entering variable. Good, I think these things are clear. Now perform the pivoting. For the new tableau, the objective row can be computed as we used to. Okay, where Ti is the jet column of the new table. Okay. Now 5, stop the process when the basic solution is visible, which means the column at the entry in the column, the right column, all of them are positive. Okay, now we go back to example 2. So we have this original primal problem, and we converted it to canonical form, and we made that table. Okay, now okay, what we do here now, notice here the solution that this table represent is this, and we have seen this before. So we have an invisible solution. Now pay attention to what I'm saying now. We will do by voting. I get a new table, and again a new table, and again a new table. Okay, at every step of this by voting, the invisible solution we have here will become visible step by step, more visible. Let me say. So we have -4 and -6. So we do the by voting, then one of these negative will disappear and will be replaced by positive. We do by voting again, then the other negative will disappear, and then we have positive, then we have two positive, then the solution is visible. So doing the simplex method now will make us make the visibility come out step by step. Okay, now let's go here. Let's do the work as we have said before. So first we go to the largest negative number, which is -4. Okay, this is the way we choose. So this is the departing variable. This shall be the departing variable. Now how we decide the departing row? So in here we'll have this to be the departing variable. How we decide that departing uh, so let's go back, take this and stay above there. Okay, so this is the departing variable. How to decide the entering variable? We will compute these ratios. 1 over -1. These are the entries in the pivotal row. And that's it. We take only for the negative. We take the ratios whenever the entries in the pivotal row are negatives, right? So here what I'm saying, the ratios are formed only for this entries of the pivotal row that are negative. Okay, so the pivotal row here is the first row, correct? And we do 1 over -1, which is -1, and this is the only ratio, right? Or what? Am I doing something not good here? To do the by voting here, we go to the smallest non-negative number in the resources vector, which is this one, -6. So this is the departing variable here. This is the departing variable. Now we divide, we take the ratios 1 over -2, which is -1/2, 2 over -1, which is -2. So which one we choose? So let me again compute here. 1 over -2. This is for column 1. And for column 2, we have 2 over -1. So this is -1/2. And this is -2. So which one we choose? So we choose that this is here what when I said the largest negative number. So let's go back. And here it says the maximum ratio. The maximum ratio. And let me write here the largest negative ratio. Okay? The largest negative ratio. So the entering variable would be x1. Okay, good. Now do the by voting. Divide this row, all this row by -2. Right? Divide by -2, and then we get that. And use the row operation or use the way of matrices as we have learned before. So we obtain the new table. Now for the new table, we have this negative only. We don't look at this one, no. So only we look at the resources vector. So a negative, and this is the only ratio we have. We need to compute. Oh, we have two ratios actually. This is one, and this is another one. So we have 1/2 divided by -3/2. This gives us -3. This is for column 3. And we have 1/2 divided by another 1/2 and get -1. This is for column 5. So we will take the, what did we say here? The largest negative, right? No, okay. I did a mistake in here. It is -1/3. It's 1/2 over 3/2. So it is -1/3, and this is the largest negative. So this will be the entering variable. And we know this is the departing variable. And then do the by voting. Make this. So in here we have chosen this. Now we chose this, make it 1. And do the by voting and make 0 the number below it. You know how to do this. Now notice here, this table give us a solution -1 and 0. The table before give us a solution -4 and -6. So we have two negatives. In the step after that, we have one negative. Now in the step after that, we will have no negative solutions. Sorry, we have here 3 and -1. So at the beginning, two of the basic variables were negative. Then one of the basic variables is negative, the other is positive. And then here, two of the basic variables are positive, and then we had reached a visible solution, and it satisfies optimality. Okay. Now, when we do the by voting, we obtain this table, the final table, and it says x3 equals 2 over 3 and x1 equals 10 over 3, and then we are done. So this is the dual simplex method. Okay, I hope all these things are clear. Okay, now what do we need this for? Okay, the principal use of the dual method in here, we mean by this method is the dual method. Why do we need to use it? Is to restore visibility when additional constraints are included in another programming problem whose solution is known. The following example will illustrate. Now, uh, in practice, first, for a practical problem, you make a model, which is a linear programming model, okay? And then you solve that model, and then you give the solution. Once you take the solution back to application in real life and do the experiments, you might find that more constraints were supposed to be added, or more constraints are needed to be added. Why? Because new things happening. Now, adding more constraints might cause the solution you have in hand to be invisible. How to restore invisibility? So adding one more constraint makes the solution we have to become invisible. How to restore the visibility? This is what the dual simplex method is about. And we will see that through the following example. Okay, so this example says there are three typical kinds of dog food that paws eat each day. Okay, dry food, canned food or wet food, and dog biscuits. The nutritional analysis of his favorite brand is given in the following table in person. Okay, so dry food will give fat 8.0, 14 for protein, 5.5 fiber, 12 for moisture, and it costs 4.1 cents per ounce. And these are data for wet food and biscuits. Okay, now what's happening here? The veterinarian has suggested that both get at least 5 ounces of protein, and this is the constraint, right? Because protein is that. So we have 14. So it says by percent. This is given by percent. So the 14 will be 14%. So let me see. This goes for the constraints in blue. Now, and at most 1 ounce of fiber each day. And this is the constraint because fiber is here. And we have at most. See, in here we have greater than or equal, but in here we have less than or equal. So this is our linear programming problem. Now his owner has set up a following linear program to model the dietary requirements and minimize the cost. So we want to minimize the cost. This is what we wanted to do, minimize, where x1 is the dry food. So this goes for x1, and this goes for x2, and this goes for x3. Okay. Now, introducing the slack variables, we give the canonical form, and then we transform this linear programming to this canonical form. Okay. Now, solving this linear programming problem using the dual simplex method. Now, work the dual simplex method the way we have just learned to this problem, and then we obtain this final table, and you need to verify these computations. Okay, so I will leave it for you to verify. Okay, So from this table, the minimum cost diet go for, okay. So this is the solution x2, and this is for x5. Now x5 is a slack variable, right? It does not represent any kind of food. So the diet must consist of this amount of wet food per day only. So the solution here and the cost is that much. So to make the optimal solution, we only needed to use one kind of food, which is wet food, this kind only. We did not use dry food or biscuits. Okay? Okay. Now what's happening after that? We have reached the optimal solution of the linear programming problem. Good? Okay. And make sure to use the dual simplex method and verify that we get this table. Now, what happened after that? At the most visit of the veterinarian, okay, now another visit to the veterinarian, she suggested that the pause, in fact, intake must be limited to this. So after another visit, there was a recommendation that the fat must be limited to this amount. This limitation were not given at the beginning. It is added afterwards. So we get a new constraint. It is fat intake. It is for fat, right? And we go back. So let me give it green. The fat shall be limited to, which means at most this amount. Now we go back to the table here. This is fat. So it is 8x1 plus 6x2 plus 8x3 with percentages. So we get this new constraint as limitation. So we add this new constraint to the original problem. And this will require a new slack variable, right? Now, take the constraint and plug it in the table. Which table? The one we have ended had a table. This one. So don't go and work it out from the beginning. Okay? So هنا انت ممكن تاخذ هذا الكونسترينت وترجع على البروبلم الاصليه وترجع تشتغل من جديد، لكن هذا الشيء راح يكون مزعج. او انه تاخذ هذا الكونسترينت وتضعه في الجدول اللي انت انتهيت فيه. So add this constraint to the very last table that gave you the solution. Okay? How we do that? So it is in here. Now it is added. Okay? Here we go. It is here. Okay? So it is added to this table. Just so we added it here, somewhere here. Okay? Now, what we do after that, the new slack variable will be basic variable. Since x2 is a basic variable, or the entries labeled by x2 must be a 0, except the entry in the row labeled by x2. Now, this is saying what? x2 is a basic variable. But look at the column of x2. You know that the columns of the basic variable shall consist of zeros, except at one place we have 1, which is the column of that variable and the row of that variable. So we have to get rid of this amount and make it 0. How we make it 0? Multiply the one with negative 0.06 and add it to the row after that. Okay? And then do the row operation. And then we obtain this table. Now what we do with this table? We do by voting. Now this caused, look in here, making the point 0.06 to be 0 caused this to be negative. Notice this negativity here. Now work the simplex method. So we will compute ratios, this over that, and this over that only for the negatives. And which ratio is the maximum, and we take it and we will find this will be the pivot, and therefore x6 will be leaving because we have x6 as an useless variable and we want to get rid of it, and x1 is entering. And now do the process of pivoting, and then we get to this new table. Now using the dual method, we may restore visibility, and this is what I have just said, and then we get this new solution, and then we are done. So x2, which means x2 is the dry food, right? So this is for x2. x1, no, sorry. This is for x1. And this is for x2. And this is for x3. Okay, so what happened here? Let's go back and review the example. At the beginning, we have two constraints, and then we work the solution, the dual simplex method, and then we obtain the solution. Thank you, we're done. But after that, we needed, for some reason, to add a new more constraint, one new more constraint. We took that constraint and added it to the table that we ended with. Adding that to the table and do the pivoting, we got a new solution. This new solution represents the situation after adding the new constraints. Then we got new solutions. Now notice that when we added the new constraint, what happened? We lost visibility. We lose visibility. What I mean, we have something negative here. So let me write that. After adding the new constraint, we lost visibility, which means we have negative here. We have this negative, and we want to restore that visibility. This is why we use the simplex method. We go to that negative. This gives us the departing variable. Do the ratios. Do the pivoting. This negativity will disappear. So we will obtain a visible solution. So I hope this is clear why we are doing or learning or using the dual simplex method. And we are done with this section.